Okay, when we're using a clinometer to measure tree height, I want you to remember two things, two important things I want you to measure. First, we're going to be measuring our distance from the tree itself, that horizontal distance, that straight line distance between you and the tree. That's relatively easy here on flat ground, that horizontal distance. We're going to measure that in feet. Secondly, we're going to need to use the clinometer to figure out what is called the percent reading from the clinometer. We're going to use the clinometer's percent scale to find the percent reading. Well, what does that mean? That means the portion of the percent scale that is taken up or occupied by our tree. Again, the portion of the percent scale that is occupied by our tree, top to bottom. So first, we're going to measure that horizontal distance from us, the recorders, to the tree itself, and we can use our measuring tape to do so. So using the measuring tape, the distance between us and the tree is 99 feet. Of course, we use the measuring tape, but if you're comfortable with pacing off the distance, you're welcome to do that as well. So what is a pace? A pace is two of your own steps. 1, 2. 1, 2. How many paces between you and the tree? You could pace off that distance as well. For me, I know that one of my paces is equal to 5.5 feet. So the distance between us and the tree, again, is 99 feet. You can use a handy measuring tape, or you can pace off the distance yourself if you choose. So we've collected the first piece of information, the distance between us and the tree. Second, we're going to figure out the percent reading from the percent scale on the clinometer. Okay, when you're looking through the clinometer, especially when you're doing it for the first time, it can be a little bit tricky. But the first thing you're going to do when looking through the viewfinder is you're going to find that horizontal black line. We call that the hash mark. Again, that horizontal black line, call that the hash mark, and we line up our 0 on the scale with that hash mark. That's what's called leveling off or leveling out, starting at the 0 point. So that's what we're doing. And if you look straight ahead and line up the hash mark with the 0, you're looking straight ahead and you have an imaginary level straight line from you to the tree. And once you're confident that you're aiming at the tree and you have the clinometer leveled off at the 0 position, then you do what's called scaling up. Move the clinometer slowly until you see that horizontal black line, that hash mark, intersect with the very top of the tree, intersect with, in a conifer, what's called the leader. So what number on the percent scale intersects that black horizontal line? In our case, we have 110 or 110%. So we have those two important measurements. We have the percent reading from our clinometer, and we have our distance from ourselves to the tree. Distance of 99 feet from us to the tree, and a clinometer reading of 110%. So we multiply those two measurements together. Oh, but wait, we forgot one thing. Since we're working with a percent reading, we have to convert that percentage to its corresponding decimal. So divide by 100. So a reading of 110% would actually equal 1.10. We multiply 1.10 by 99 and we get 109 feet. So this tree that we've been measuring, this giant sequoia, is it 109 feet? Well, almost. We have to add one last thing to our measurement. If you recall, I asked you to point the clinometer straight ahead and level it out. If there was an imaginary line shooting off from the clinometer right now, what it would do is intersect the tree above ground. In fact, if I were standing right next to the tree, that imaginary line would be intersecting my head. So the last thing you do when you're measuring tree height on level ground is to add on the height of the recorder, the height of the measure, or in this case, my height. I'm 6'2", and that's 6.17 feet. And if you want to round to the nearest foot, which is what we'll do in these examples, you can add on 6 feet. So the height of this giant sequoia is 109 plus 6, or 115 feet tall. So is there another option besides adding on the recorder's height at the very end of the calculation? Well, there is another option. You don't have to add your own height. I mean, who's to say that we couldn't level out the clinometer and then scale down and see what percentage corresponds with the very bottom of the tree? You could do that as well, but recorder shake is a real issue. When you're first learning how to use a clinometer, the scale moves quite a bit as your hand shakes. So sometimes it's a bit annoying to try to capture that last percentage since your hand is shaking quite a bit. So because of that, I like to simply add on my own height at the very end of the calculation. So if we wanted to focus more on trigonometry as we wanted to determine the height of this tree, we could do so, again with the aid of our clinometer. I want you now to imagine a right triangle formed by the ground and the tree itself. Well, rather than imagine, why don't we just look at a drawing? Here's what I mean. So as you can see, two of the sides of the right triangle include the ground between us and the tree, that's one side, and then the tree itself is another side of this right triangle. And those two lines form what's called a right angle, 90 degrees. So we have a right triangle. So if you think about a right triangle and those old trigonometric functions, sine, cosine, tangent, etc., sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. Well, what is a hypotenuse? Well, it's that invisible line connecting me to the top of the tree itself. That's our hypotenuse. So we're going to use what's called the cosine function. Cosine of theta is equal to adjacent side over hypotenuse. Well, theta, what the heck is that? Well, that's a terminology we're going to use to represent the angle that we're going to be measuring. In our case, we're going to be measuring what's called an angle of elevation, using the clinometer to do so. So again, I'll ask you to look through the viewfinder of the clinometer, but this time we're going to be working on the left-hand scale, what's called the degree scale. Again, zero out your clinometer, that black horizontal line, line that up with the 0. Now you're going to be moving the clinometer up once again, but this time you're going to be reading the number that corresponds with the left-hand scale, the number that intersects that black horizontal line. That's going to be your degrees. And in this case, our angle of elevation is 48 degrees. So in terms of our right triangle, we're going to have cosine of 48 is equal to adjacent over hypotenuse. And the adjacent side is going to be that ground distance that we've already measured. So in our case, we're going to use the cosine function to find out the length of the hypotenuse. Again, the hypotenuse is that imaginary line connecting me to the top of the tree. We're going to use the cosine function. Remember, the cosine function from trigonometry is cosine of our angle of elevation is equal to our adjacent side over hypotenuse. Our adjacent side, again, is that horizontal distance we measured, 99 feet. So we have cosine of our angle of elevation is equal to 99 over hypotenuse. Let's isolate that hypotenuse on one side of the equation.
With the hypotenuse thus isolated, this is what we have. Hypotenuse is equal to the adjacent side, our horizontal distance, which is 99 feet, over cosine of 48 degrees. Referencing a cosine table, or simply a calculator if you have one handy, we find that cosine of 48 degrees is 0.6691. Plugging that in, we get hypotenuse is equal to 99 divided by 0.6691. Our answer is 147.9, which we will round to 148 feet. Finally, we can use the sine function from trigonometry to figure out our tree height. Recall that the sine function is equal to opposite over hypotenuse. In our case, that opposite side of the triangle is our tree, so we can call it tree height in this simple equation. we already know that our angle, theta, is 48 degrees, and we've just determined that our hypotenuse is 148 feet. So our equation becomes sine of 48 degrees is equal to tree height over 148 feet. Referencing a sine table, or once again a calculator if one is available, we find that sine of 48 degrees is 0.7431. Carrying out the basic algebra, we see that tree height is equal to 0.7431 multiplied by 148, which gives us 109.9 feet. We can round that to 110 feet. And finally, as in our first example, we'll once again add my height of 6 feet right at the end, since we are on level ground and the clinometer is recording its numbers 6 feet off the ground. This gives us our final tree height of 116 feet. So for all intents and purposes, we arrive at roughly the same tree height using the two methods. I recommend carrying out the latter method if you want the calculations to center on trigonometry to a greater degree. Regardless, you'll discover that trigonometry plays a significant role when determining tree height on a slope. This is what we'll explore next.
Determining the height of a tree on level ground is fairly easy, but things start to change a little bit once you insert a slope into the equation. So how do we determine the height of a tree that's found on a slope? In this case, how do we determine the height of a tree that's found upslope from us? Well, some things haven't changed. We still need two basic pieces of information. We need to determine our distance from the tree, again the horizontal distance from us to the tree itself, and then our clinometer percent reading. Again, the portion of the clinometer percent scale occupied by our tree. So what's important to remember here is that as far as distance from us to the tree, we need the horizontal distance. That is not going to be the same as simply walking up to the tree itself and recording that distance, because that is not a horizontal distance. That's what's called a ground distance. It's going to be the hypotenuse of our right triangle. So this is where trigonometry comes back into play. I want you to imagine a right triangle superimposed over the landscape here. So in terms of that right triangle, I want you to imagine the tree that we're going to be determining the height of. Imagine the trunk of that tree extending down deep into the ground. That axis forms one side of our right triangle. The horizontal distance, that straight line distance between us and that axis of the tree, would require that we dig into the ground in order to actually measure that horizontal distance. We can't do that. So we can't measure that horizontal distance directly. But working with trigonometry, working with the cosine function, and measuring those things that we can measure is going to help us determine the height of the tree and determine that horizontal distance that we need. So, collecting two pieces of information first. That ground distance, walking up with our measuring tape to the tree itself and documenting that distance in feet, and then measuring the angle of elevation between us and the tree itself.